Okay, well, my thanks to Selina and the other organisers for setting up this workshop and for giving me the chance to speak. I'm going to talk on the subject which hasn't been much discussed, and I'd be interested to get reactions on it. The question of whether or not we can explicitly make sense of the notion of non-locality in the gravitational field, and if so, whether we can experimentally test and how well we can experimentally test for non-locality. I'm going to refer to various papers, but the first one is one of mine, which was given at a meeting in Perimeter a couple of years ago in honour of Anna Shimony, published in the Proceedings there. And the basic ideas I'm going to talk about, at least in the first half, are set out in that. So I want to argue, I guess, four things. First, that if we have a theory that describes a gravitational metric, and we're not committed to the precise form of that theory, it's presumably not going to be general relativity, since that doesn't even have a quantum theory. And perhaps it's an effective theory in which the metrics only define a reasonable scale, or perhaps it's only an approximate theory. But nonetheless, we have some theory that assigns probabilities to finding spacetimes with particular metrics and matter distributions. I want to argue that the first point, that it's a sensible question. We can define mathematically the question of whether the metric does or does not have non-local correlations. Of course, there's a long discussion already in the physics literature, going back famously to John Bell, and many experiments testing for quantum non-locality. And I think a natural temptation, first response that might come to mind, is that if this question does make sense, then we already must know the answer. It must follow already from standard Bell experiments. I want to persuade you that that's, in fact, not true. Standard Bell experiments may or may not bear on your intuition about the answer, but it isn't directly deducible from any standard Bell experiment. But I want to go on to argue it can or could, in principle, be resolved by non-standard Bell experiments, by a new type of Bell experiment. And more than that, I want, since some experiments, at least in this direction, have actually now been done, I want to describe them and summarise what they've taught us. So let me start with the notion of local causality. Local causality was originally defined by Bell and Shimony and others, trying to flesh out the intuitions that underlie Bell's original papers on Bell's theorem. It was defined as a property of theories describing events in Minkowski spacetimes, so it said nothing about more general spacetimes. I want to give them a definition, and I don't claim it's necessarily the only possible one, but a definition that seems natural enough that extends the notion of local causality to metric theories. So I'm going to take as given here, as I've already hinted, that we have some theory to talk about, and that theory gives us probabilities for spacetimes. It may give us probabilities for a complete spacetime only, and we have to work out everything else from that. It may give us probabilities for incomplete partial bits of spacetime. And it gives us fundamental probabilities in such a way, and we're not going to be committed to any details here, in such a way that we can define quantities of this form. Probability, and this is a notation I'm going to use repeatedly here, probability of kappa given lambda, comma, and r, where r is a relation that depends on kappa and lambda. The idea is that from the theory, somehow or other, we can calculate the probability that spacetime contains a region isometric to some reference region kappa with a metric set up on it, given that the spacetime is known to contain a region isometric to lambda, and given some relationship, which we obviously need to spell out, between the regions lambda that it's known to contain and kappa that it might or might not contain. And we're going to code that relationship as R and kappa lambda. I should here recall my thanks to Faye Dowker, who very helpfully clarified my thoughts on this and set out the basic ideas from which the definition I'm going to give set out. I should at the same time say that my use or abuse of these definitions is my own responsibility and application is own responsibility. There's also earlier related work in papers by Johansson and Van Raadt and Sorkin, and I'm sure others. So I'm going to care in particular about the following sorts of conditional probabilities. Here's the first one. Probability of kappa given, well, this is really telescopic shorthand now. Lambda perpendicular sine lambda prime. What does that mean in words? Probability that we have two regions, lambda and lambda prime, which are both past regions in the space-time. Past region bit is this last thing here. They're unionizing space-time. They have space-like separated domains of dependence, and the domain of dependence of lambda is isomorphic to kappa. So forget about kappa prime for the moment. We're talking about a space-time which contains something like this. Lambda overlapping with lambda prime. They're both past regions. They both contain all the past curves going through points in them. And we're asking what the probability is that in this space-time, the domain of dependence of lambda turns out to be kappa.
You did?
Yeah.
Before you said, I have a question about the first slide. You mentioned that the local causality was defined by Bell and so on and so forth, but you forgot that local causality was defined by Einstein long before Bell. And Einstein didn't define it in terms of probability, neither did Bell in terms of probability in his first paper. So why are you starting with probabilities?
This may be one of these coffee time questions rather than mid-seminar questions. Because I want to talk about the relationship with Bell experiments and all of which are analysed in terms of probability and conditional probability.
But that's what I'm questioning, that you are already smuggling in something. So it is
smuggling is a loaded word, but you're right to make the point. I'm using probabilities. Yeah. Okay. Here's a second thing that's a bit of quantity that's of interest. Probability of kappa given lambda perpendicular to lambda prime semicolon kappa prime. Well, again, that's just compressed shorthand. What it means is everything that we said before, but one extra condition. We know now that the domain of dependence of lambda prime is isometric to kappa prime. So we're asking, in the end, whether this are necessarily equal in our unknown theory. Does the fact that you know how lambda prime gets completed bear any relation, make any difference to the probabilities of how lambda gets completed? And I want to say that the theory is locally causal if these two quantities are A, always well defined, and they, of course, in the general theory, they may not be well defined, but I want to assume that they are here. They're always well defined, and they're always equal. And it's not locally causal otherwise. GR obviously is locally causal because all the probabilities are either 0 or 1, and the probability that the domain of dependence of lambda is kappa doesn't depend on anything to do with lambda prime or kappa prime. Quantum theory, as Bell famously showed, is not locally causal in his sense, and the above definition is intended to generalize his sense from Minkowski spacetime to more general spacetimes. And when, as I've mentioned, one might therefore be tempted to assume that all the Bell experiments that have been done to date that were testing quantum local causality were also testing gravitational local causality. I would persuade you that's not true. So let's take a look at a standard schema for a Bell experiment. We have some source here of entangled particles, let's say they're photons. They go left and right. They're detected by measuring some variable which is chosen locally and randomly, detected in photomultipliers, let's say, which produces a little electric pulse. Filters tell us what exactly we're measuring, which polarization. The signals from the photomultipliers go along wires back to some coincidence counter which analyzes the data and prints out a nice graph which gets published in PRL. That's roughly a Bell experiment. Notice there isn't really much that's affecting the gravitational field in any detectable way in any of this story. All we've done is have a photon going into a photomultiplier generating a tiny, tiny, tiny little current. certainly in practice, there's no way that we can detect the gravitational effect of that. Perhaps even in principle. We don't know because we don't understand quantum gravity, but one can try and make back-in-the-envelope tests, and certainly according to some of those, even in principle, there is simply no discernible gravitational difference between different possible outcomes for measurements on the left or the right here. And worse, and I don't mean to be heretical here, but I do mean to be careful. Worse, if we take the admittedly contentious view that quantum theory involves a transition from something that's potential, not necessarily physical, the wave function, to something that's actual, a classical measurable outcome at some scale which is at the moment uncertain to us. We don't generally understand what that scale is. And you press the logic of this rigorously through, you persuade yourself that standard Bell experiments don't quite necessarily even establish quantum non-equality. They don't even quite do what they were supposed to do. I don't mean to be heretical here, I mean to point out that there's a little loophole which needs to be discussed, and I want to go on to discuss it and explain how to close it. So the loophole is known as the collapsed locality loophole, first described in this paper in 2005. Here it is in a nutshell. Here's our Bell experiment schema again. The worry, the potential worry, is that we have a quantum state describing entangled particles up to here, and that we continue on still finding that the appropriate way to describe the experiment, even after the photons have gone through the photon multipliers, is entirely at the quantum level, is entirely at the level of an uncollapsed wave function. So that we set up, so to speak, faux non-local correlations. So non-local correlations, absolutely, but they're there in the wave function. Nothing, so to speak, real has actually happened and been correlated. And we can pursue things here. And the collapse takes place in the coincidence counter or later on. We do not get two separate collapses at space-time separated points, which allow us to infer that genuine inequality arose. So, yeah, this is just to reinforce that point. The collapse takes place either here or sometime later. But as far as we could tell, perhaps at one point rather than what we were hoping for here and here. Okay. Let me stress some motivations pro and con. The first is, although this is a loophole, presumably, like most loopholes, it will be closed. It's different in flavour, at least to my mind, from most of the standard loopholes, in that it does at least test quantum theory against some other theory which is internally consistent. It's a surprising fact, and I haven't got time to discuss it here, but it's a truth that you can make sense of a purely locally causal version of quantum theory. It's a very strange theory, it has some very unfamiliar properties, it's very probably refutable by experiment, and very probably has been refuted if anyone knows where to look, but it isn't logically inconsistent. So there's some motivation, some extra motivation from the fact that you have, at least principle, two different theories that are being compared. A second motivation is that you might, if you're interested in the game, or trying to build some hybrid theory that involves classical gravity and quantum matter, you might well start by thinking your task would be a lot easier if your classical gravity at least were to behave locally causally. At least then you could start to write down dynamical laws for the metric without having to worry about non-local correlations in your dynamical law. Well, maybe that turns out to be true, maybe it doesn't. It's a speculative motivation. So we can think of tests of gravitational locality, that's what I'm about to describe, with two different motivations in mind. One is we're directly trying to verify a property of the gravitational field. It doesn't have non-local correlations. Another, we're trying to close a stubborn loophole in Bell experiments. Let me leave that caveat for question time. So having claimed, let me make some disclaimers. I'm not here to talk to you because I have some aesthetic or other objection to quantum non-locality or to Bell correlations or to the standard understanding of these things. I don't see any compelling objection to quantum non-locality as usually understood. I don't see any compelling reason why the gravitational field can't have non-local correlations in the sense I've just defined. I just think we would like to be sure. These are questions that are of really fundamental interest, and the quantum in particular, at least my personal understanding, is so hazy that I just don't know where the boundaries of what's conceivable and what's not so conceivable really should be drawn. It seems only sensible, if we possibly can, to try and test and verify beyond all reasonable doubt. And we might all have very solid intuitions as to which way things should work out. I certainly do. But my reading of the history of science is that just once in a while, even distinguished and collected groups of physicists can be wrong. Nature can surprise us. So it's worth doing experiments. And happily, the Geneva group, headed by Nicolas Gisin, with this particular experiment run by Szalár, more than anybody else, have done what I think is a very beautiful and intriguing experiment that at least gives us some solid and interesting data in this direction. This was published, well, you've seen it, it was published at Piro a couple of years ago. So they had two brilliant ideas. The first is, instead of using a photodetector and a signal which is just current, which doesn't really move anything about macroscopically, to register the result of the experiment, one could use a piezo crystal. So you take the signal from the photodetector, run it through the crystal, and the crystal very, very quickly responds, it deforms. And their second brilliant idea was to attach a mirror to the end of the crystal so that you can measure that deformation directly, very, very precisely, very, very quickly by interferometry. So the crystal's here, it either does or doesn't deform, like that, and the interferometry tells you whether it has or it hasn't. And the setup is that you have these devices, these piezo plus mirror plus interferometer devices, attached to photodetectors on both wings of the experiment. And another key ingredient here, we have a pretty large scale separation between these two wings, 18 kilometers in this case. So the claim is that combining two such things in a Bell experiment on this scale, on this macroscopic, mega macroscopic scale, 18 kilometers, allows us actually to directly confirm that we get Bell correlations among the deformations of the piezo crystals on the left and on the right, and to do so and complete our confirmation in regions that are space-like separated here and here. So let's look at the figures here. The time from the photon first going into the photodetector to the mirror actually displacing or not displacing is given by this figure here, so 6.1 microseconds. The displacement is at least this big. Not huge, but significant, 12 nanometers or so. And the mirror isn't hugely massive, but again, it's not a trivial mass, it's 2 micrograms. So I'll copy those figures again here on the left. Is that collection of numbers enough to ensure that if we started out with a quantum superposition of gravitational fields, they would collapse quickly enough that we'd really have a genuine test of space-like separating collapses? Well, that's a debatable and unfortunately model-dependent question, because again, we don't understand quantum gravity. But there are at least a couple of well-known models, albeit, to my mind, ad hoc models, and certainly I think their authors would agree only partial models, incomplete models, due to Roger Penrose and Laios Giossi, which give us some back-of-the-envelope time for how quickly they think the collapse will take place under these circumstances. So the collapse here depends on the volume of the mirror, V, depends on the mass of the mirror, M, and it depends on the displacement between the two possible states, D. Depends in this way. There's a factor of 2 between there, but and I think I forget. So I think this is Penrose's and Joshi's is a factor of 2 larger, but please don't shoot me, it's the other way around. In any case, put all that together, you end up with 1 microsecond, making a total time from the photon entering the detector to collapse of 6.1 microseconds plus 1 microsecond or so, which we should compare with the time taken for light to go between the 2 wings of the experiment, 60 microseconds. So if we take this estimate at face value, we have for the first time a direct test of non-local correlations of the gravitational field. And what does the data show? Well, they confirm what I think, I'm almost sure most people's intuitions suggested, that we do indeed get dull correlations here. The relevant curve is this bottom one on the right. That's counting the coincidences. The stuff at the top is all the cases where they measure something on one side or the other, but not on both. And there's actually, if you look at the figures here, there's actually hugely more of those, but they just all have to be thrown away. So per minute, I think we get about 250,000 single counts and about, well, on average 50 coincidence counts. So be it. Well, to my mind, it's just wonderful to be able to see experimenters with their own ingenuity getting something from nature, getting something that I think, in a small but genuine way, is something new from nature, something we haven't previously tested. And it's a beautifully designed first test of gravitational non-locality. But it does fall short of the ideal in various ways. The first, most obvious one is the Penrose-Giossi collapse criterion itself. It's a ballpark figure. It's nice that we can work with it and find we can fit it in an experiment. But it is really, it seems somewhat ad hoc. And I'd be very interested to hear people's suggestions, but I don't feel I could confidently say that there's a way to produce a truly compelling criterion from theory alone at the moment. But for me to, at least, I'd love to hear somebody say that they can be confident and say why. So failing that, what we would ideally like to arrange is for outcomes of experiments in the 2 weeks of experiment to correspond to gravitational fields which we could directly distinguish by measurement, and to be able to complete all of that, creating one of 2 or more possible fields and measuring those fields directly, still within space-like separated regions. That's, yeah.
I'm sorry, maybe everybody else understands the logic, but I'm missing any mental logic. You claim that if it were not for the Penrose-Giossi collapse, that the standard result would not have been obtained? That is, the 2 mirrors would have remained in a certain position and would have disrupted the standard result? Is that the logic?
I'm not quite sure what you mean by disrupting the standard result, but if you mean what I think I mean, then no, that's not what I'm saying. So let's retract.
How is the analysis of the gravitational superposition playing a role in the analysis of the experiment?
So we're having to take Penrose and Giossi's word for it that there's been a collapse in this short enough time in order to be able to go on and be able to claim that we've generated a gravitational field here and a gravitational field here as a result of this measurement process, and we genuinely created 1 of 2 distinct fields and got the right non-local correlations.
Right.
Now,
so my question is, supposing that the time, supposing the mirror was 1,000 times wider,
yeah.
so you would expect the Penrose-Giossi collapse not to have happened by the time the photons come. It's perfectly possible somebody might construct such a mirror.
Sure.
Then is there no other decoherence effect which would have decohered the two states of the mirror?
Quickly enough.
Yeah.
Well, I guess we'd have to sort of, we'd have to look at that case by case. But there are two questions. Could you decohere the states of the mirror, and then would you have produced different gravitational fields as a result of that decoherence? The answer to the first, not clear, but the answer to the second, according to Penrose Giosi, would be no. These are just not macroscopically distinct enough for us to be able to distinguish the fields in short term, if I understand.
Okay,
So, but the claim isn't. Carry on. Sorry. What do you tell?
Just state, because I don't want to disrupt your talk.
Okay. Well, just to be sure there's no misunderstanding. I'm not saying if the mirror were smaller, something really spooky and creepy would have gone on, and we'd have refuted the standard understanding of experiments. We just would have failed to close this particular loophole. We just would have failed to test the thing that we wanted to test that hasn't been rigorously tested before. Okay. And so to press on and to really nail down, really fill in this loophole, we may have to wait for long-distance space-based experiments in which you can separate light minutes or light hours if you need to, and take the time you need to actually generate distinct gravitational fields and measure them correctly. So, this is some interesting open questions here. My first inclination, of course, was to visit, is Hamburg the relevant port? But I heard the sad news on the BBC today that Paul the Octopus is retired from making predictions of any sort now. So we're left to our own devices, I guess, to resolve them. I don't know the answers. I'd love to. I don't even have clear way forward in thinking about answers. So if anybody has any thoughts, I'd love to hear them. Did we need to do this? Could we verify gravitational non-locality another way by thinking about what the failure of gravitational non-locality would imply in cosmology? Should we expect to see something anomalous if, against our expectations, the gravitational field were in fact locally causal? Are there more compelling criteria than Penrose Giosi? If we're going to press these experiments through to their logical conclusion, how fast can we do it? This is a technological question for technologists, really. How fast can we create and then directly discriminate between gravitational fields that depend on the outcome of quantum measurements? And does one of the motivations, as sort of speculatively hinted at, actually apply very forcefully? Is there any natural, locally causal hybrid classical quantum gravity and matter theory out there? If not, it doesn't really, it doesn't affect the other motivations. But I thought I'd throw it out there once. Right, and that's all I really wanted to say. Thank you very much.
Questions? Yes. I'm going to ask a really dumb question.
It always worries me with
the
stuff
reason
like
why
that.
I'm going to ask a question is because I've heard the word non-local used in various contexts. Field theorists would. So this is a non-local field theory because you have non-trivial kinetic terms, and so some people are actually playing around with very simple field theories, like a scalar field theory, where you have a square root under the kinetic term, for example, and they'll call that a non-local theory. Okay.
Right.
And and obviously, is that the same type of non-locality as the non-locality you're talking about? The reason why is because people have been trying to resolve the cosmological constant from things like this using such non-local theories. So that's a cosmological connection.
Yeah. We got ourselves in a mess somewhere in this terminology about non-locality. Let me see if I can. So no, I'm not using it in that sense. The idea here is something like this, that we have a... Let's forget about gravity for a moment and go back to standard quantum theory. I suppose you've got just regions of Minkowski space set up like this. Let me call that C. Okay, I need two regions that are space-like separated. So I'm going to bit with this. Okay, so these two regions are space-like separated, C and D. This is, sorry for my calling freehand drawing, but these are supposed to be light lines here. So we can think of, as a general question in quantum theory, you start with perhaps some stuff that's coming from some source or sources. You carry out measurements, experiments of any type within A, and you get data from observations in A. And you can ask, and then you're going to carry out more measurements and get more data from observations in C. You can ask whether the probability of any particular outcomes in C, given the outcomes you already had in A, whether or not that depends or can possibly depend on anything that happens in D. So there's probability of outcomes in C given outcomes in A. Well, if it doesn't depend on, cannot possibly depend on what happens in D, then we've got to have this equation satisfied. The probability of outcomes in C given outcomes in A is the same thing as probability of outcomes in C given outcomes in A and anything that you do in D. So let's put a question mark like that. Is that true? Well, it's true in classical mechanics. It's not true in quantum theory. If you have a source of entangled photons, you carry out measurements in both C and D, this equation fails, the conditional probability fail. That's what Bell and Chimney and others meant by local causality, roughly speaking, and that's what I mean here by local causality. So that's rather different from having a non-local interaction in the field of theory. That might be one way to generate a failure here, but you don't actually need it in order to generate it.
You can't stand the signal.
Yeah. Thank you, Jeff. Yes, indeed. So the important difference between local causality breaking down and actually a non-local signaling breaking down. Quantum theory doesn't allow you to send signals faster than light, but it does allow local causality.
Okay, whereas in this particular case, some of these non-local theories...
Some of those non-local theories would valid.
K and then drop. Yes. Yes.
Measurements of the gravitational field, because, well, it's very difficult to think about these piezo crystals, but if we just scale everything up and imagine an experiment in space that we'd like to do, we can make these measurements result in very large displacements of very massive things.
Yep.
Right? So instead of the mirror moving a few nanometers, we could imagine some planet moving a large distance.
Yeah,
so long as
yeah.
we keep them far enough apart.
Sure, you can blow a planet or not depending when you go 0 or 1.
So what you're having us believe is that, so the planets move, quantum measurement, which is now long over. I mean, if we make them far enough apart, we can wait for ages before we actually measure, the planet moves, and then, half an hour later we measure the gravitational field. Just because there was this quantum measurement in the past, now, when we measure the gravitational field, we don't get the expected result that we ought to get if general relativity, which I mean gravity, is true. Is that fair?
No. So let me take this point by point. First, I mean, there's a trivial sense in which, of course, you're right. I'm questioning whether general relativity, but it's not the sense you just outlined. If we have pure general relativity, nothing quantum anywhere, no entanglement, then we have no need for probabilities. It's purely deterministic theory, and as I said way back in the talk, general relativity is locally causal. So you're right, of course, in that relative to what you were just saying, trivial sense. There's a querying of general relativity going on. General relativity is not the complete underlying theory. The possibility you just outlined sounds science fiction, but you're missing another one, which I think, it's hard to sort of debate about degrees of implausibility, but you're missing another one anyway, which doesn't bear on general relativity. We could find that when we do Bell experiments the normal way and bring the data together and don't blow anything up gravitationally, the coincident cancer shows us non-local correlations. When we do the experiments and everything is hooked up so that we're blowing up planets, or at least moving things macroscopically enough, we can detect gravitation. We no longer see non-local correlations. We see something different. Now that's you may be sceptical about that. It's certainly not my guess as to how things could work either. But that doesn't bear on the point you just raised about the gravitational field behaving in some way that, even at the macroscopic level, has nothing to do with the expectation you've got from Newtonian gravitational general. So there is more to say, but do you agree with that? Do you agree that that's another thing that's clearly being tested here that has nothing to do with one factor?
Are you saying then that suppose we don't measure gravitational field, we just move the planets, and then we just have someone say whether the planet is here or here? We don't actually have a torsion belt, whatever it is that we're getting. We just have someone record it in a piece of paper. Would there be non-local? Is the possibility that there are or there aren't non-local correlations?
We can talk about loopholes on top of loopholes on top of loopholes. But let's start with the most straightforward one. Whether we actually measure the gravitational fields or somebody reports it, there are no non-local correlations. Once the experiment is set up so that we blow things up to macroscopic gravitational scale.
Joao, and then.
Well, I have a question which ties in with the one Stefan asked.
Okay.
So to go back to cosmology, no doubt this mechanism between locality and relativity. Is there any theory saying that the kind of non-locality you discussed would never possibly, like an overall theory, that it could never possibly generate a scaling spectrum or generate homogenized universe? So is there actually an overall theory?
That sounds like a lovely question. I'm just not competent to answer it. I was
I think
hoping
there
you
is.
just might.
It's a form of no signaling theory.
Sorry,
Well, so if the question is there can we prove no signalling from this non-locality? The answer is yes, but I'm not. I don't know how that
there are actually theorems about
pans out in cosmology.
There are theorems about the kind of power spectrum you can have if you just move macrocausally around. And in that case, of course, it's a very spectrum. So you know exactly what the index can be. So it would be really nice if there was something exactly adapted here and say, expect the limits has to be bigger and these are smaller than that. Or whatever. I mean, really obvious things are good, but I don't know if there is enough information to write a theory like that.
This is why we should have meetings like this. For people like me to be taught things in cosmology they don't know. So I can't answer the question, but I agree it's a great question. I sort of hope and expect other people here probably can answer it.
So You were talking about gravitational induced collapse, and you were using this Penrose DLC.
As one line of motivation.
Okay, so
you
you-
in discussion, yeah.
And you're wondering if there are any other possibilities.
Mm-hmm.
And so, have you yourself considered any more?
Oh, look, I tried, but there's a reason why I haven't published anything.
Well,
Yeah, so
the idea of decoherence to induce a collapse-like behavior is quite old, and there are proposals that couple massive systems to the surrounding gravitational fields and that could produce decoherence. I mean, I'm aware of calculations that have been done for decoherence for charged bodies, for example, in electrodynamics. And this is done in quantitative ways. And I know that there are proposals to do the same thing for massive bodies coupled to ambient gravitational fields. Like people like Bernard Kay and Charles Lawrence have proposed these.
Have proposed to do it or have done it?
No, to analyze the decoherence of massive bodies coupled to ambient gravitational field. So as the mechanism for decoherence. And I mean, at least like I said, in the case where you consider charged bodies coupled to electromagnetic fields, they have quantitative estimates for how long decoherence should take, depending on the charge configuration. So I presume similar estimates could be made for gravitational decoherence, although I'm not aware of precise calculations.
Yeah.
So that could be
I get
the last thing.
I should know more about this, or I'd like to know more about this than I do. But we ought to. There's an important distinction between proposing a fundamental new decoherence law that doesn't follow from what we already know about
It
interactions.
follows from
And
taking gravity into account
from taking gravity
from the beginning.
Yeah. So it's in that sense it's fundamentally different from Penrose and DLC.
Yes.
That sounds fruitful territory to mine. So but maybe you can give me some more references afterwards.
I suggest, we cut it here and then you can discuss. Sorry, but we are already running late. We have only 10 minutes left until we recover from back for the thing. So let's